Hello everyone, I'm Qiliang Li from University of Science and Technology of China. In this work, we propose an efficient disk failure reconstruction mechanism for large disk enclosures based on RAID 2.0. In the era of explosive data growth, large disk enclosures are widely used to provide large capacity storage. Conventional RAIDs like RAID5 and RAID6 face the problem of slow failure recovery. For example, when a disk fails in RAID5, the reconstructed data is written to a single backup disk, which is the bottleneck of failure recovery process. To overcome the bottleneck of writing reconstructed data to a single backup disk, a RAID 2.0 divides the storage space of each disk into data space and hot spare space, where data space is used to store data in normal state, and hot spare space in each disk stores the reconstructed data in case of failure. So all disks in RAID 2.0 participate in writing the reconstructed data, which speeds up the failure reconstruction process. In RAID 2.0, the storage space of each disk is divided into chunks. It constructs a RAID group with randomly selected chunks. For example, here one chunk is randomly selected from each of D0, D2, and D4 to construct a 2+1 RAID group named group 0, and then group 1, group 2, etc. in the same way. This way achieves storage load balance among disks with huge volume of data. When a disk fails in RAID 2.0, all lost chunks denoted as recovery tasks are pending for being reconstructed. Due to limited memory capacity and CPU resource, RAID 2.0 performs reconstruction in batches, each batch with a limited number of groups. The existing failure recovery schemes tag groups with successive serial number into a batch and write the reconstructed chunks to randomly selected disks. For example, when disk D0 fails, the lost chunks on D0 are reconstructed in batches. The first 6 chunks are reconstructed in the first batch. While reconstructing the first 6 chunks, due to the imbalanced data layout within a batch, the read load among surviving disks is imbalanced. For example, 4 chunks are read from D2 and no chunks are read from D3. Meanwhile, the write load is also imbalanced because the disk for writing a reconstructed chunk is randomly selected. In this example, 2 chunks are written to D4, while no chunks are written to D2. To measure such local load imbalance in a batch, we define load balance rate lambda, which is the ratio of the maximum number of chunks read from or written to a disk to the average in a batch. In this example, both lambda read and lambda write are 2. We have conducted extensive simulations to show the local load imbalance for random data layout read R, using the system time as random seed. The figure shows the average lambda read and lambda write of 100 batches for 6+1 read groups with disk pool size ranging from 20 to 100. We find that lambda read is around 2, which means the max read load is around 2 times the average. And the lambda write is around 4, which means the max write load is around 4 times the average. Such local load imbalance in a batch can be well eliminated by designing a dedicated data layout, which guarantees uniform data distribution for balanced failure recovery I/O. However, this kind of approaches have some limitations. First, the dedicated data layout is not deployed in most of the existing systems. To exploit its advantage, we should reallocate almost all chunks in the system, which is intolerable. Second, some common operations, like failure recovery or system scaling, will break the data layout. We should migrate chunks among disks to keep the dedicated data layout, which induces heavy load of data movement. Third, dedicated data layout is static and can be applied to the heterogeneous cases. So based on the above analysis, we want to design a reconstructed mechanism towards 2 goals. First, achieving local read and write load balance in reconstruction. Second, being applicable to heterogeneous rebuilding bandwidth. To the end, we propose an efficient reconstruction mechanism called RAID. It consists of 2 steps. In the first step, we batch tasks out of order to balance read load for failure reconstruction. In the second step, we select surviving disks based on matching theory to balance the write load. In step 1, we first initialize the batch with successive serial numbers. Then we get the read load of each disk and lambda read. If lambda read is not equal to 1, the read load of the current batch is imbalanced, and this batch of tasks should be adjusted. We select a task TR from the current batch to be replaced, and a task TL from the remaining pending tasks, then replace TR with TL. We keep replacing until lambda read is 1 or there are no satisfying replacements. The replacement rule is explained with the following example. For example, we add the first 6 tasks to the current batch. Then we get the read load CI of each surviving disk. The larger CI is, the hotter DI is. Here C2 is the largest, so D2 is the hottest disk. The lambda read is 2, which means the read load of the current batch is imbalanced, and this batch of tasks should be adjusted. The tasks reading from the hottest disks are considered to be replaced. In this example, T0, T1, T3, and T4 are considered to be replaced. We calculate the priority PJ for tasks reading from hottest disks. The larger PJ is, the more imbalanced read load for reconstructing TJ causes. The tasks with max PJ is to be replaced. Here we choose T1 to be replaced. Then we select one task from the remaining pending tasks, which does not read a chunk from each of disks with max PJ or max PJ minus 1 for reconstructing the task. For example, there is a task T8 whose available chunks are on D3 and D6, so reconstructing it does not increase the read load of D2, D4, and D5. Therefore, we choose D8 as TL. We replace TR with TL and update the read load of each disk. In this example, we replace T1 with T8, and the lambda read decreases to 1.5. We repeat the above replacement until lambda read is 1 or there are no satisfying replacements. In this way, we can migrate the load from the hottest disk to the lighter disks. Once we have packed groups into a batch, it will read source chunks into its memory and reconstruct the lost chunks. Now the reconstructed chunks are ready to be written to surviving disks. We should select a disk for writing each reconstructed chunk. Our objective is to carefully select the disks for balancing the write load. We first construct a bipartite graph based on the selected batch of tasks and find a maximum matching and distribute the reconstructed chunks to disks based on it. We construct a bipartite graph where the vertices represent the tasks in a batch and surviving disks. Due to the restrictions on reliability, chunks from the same group should be stored in different disks. For each task in a current batch, if the reconstructed chunk can be written to the disk, then add a directed edge from the task to the disk. After the bipartite graph is constructed, we find a maximum matching in the bipartite graph by calculating the next flow in the constructed flow graph. Corresponding to the maximum matching, we write each reconstructed chunk to a dedicated disk to reach write load balance. When applying DRAID to heterogeneous rebuilding bandwidth, we get the available rebuilding bandwidth BI of each surviving disk at the beginning of each batch, and add weights based on BI into step 1 and step 2. In particular, we substitute the counter in step 1 and change the capacity of some edges in step 2. We implement DRAID in a local cluster of 11 nodes and evaluate the recovery performance against the single disk failure with the default configuration of 50 disks, 6 plus 1 read group, and 49 tasks in a batch. The comparison baseline contains 2 randomized data placement schemes, read R and read H, and 2 conventional organizations, read 5.0 and read 5C. In offline rebuilding, we measure the recovery throughput by varying disk pool size and batch size. RAID improves the rebuilding throughput by 51% compared with RAID-R and still has 11% improvement of RAID-R with batch size of 294. In online rebuilding, we measure the request latency by replaying traces and rebuilding throughput with varied rebuilding bandwidth. Compared with RAID-R, RAID shortens the period of performance degradation by 28% and improves the rebuilding throughput by 59%. To conclude, we find local load imbalance within a recovery batch slows down reconstruction process in RAID 2.0. We propose an efficient reconstruction mechanism called RAID, which selectively packs recovery tasks into a batch to achieve reconstruction load balance. The results of extensive experiments show that RAID increases rebuilding throughput in offline rebuilding and varied rebuilding bandwidth. Thank you. Any questions?